So welcome to this video. So in this video we're going to be having a look at spin. We're going to be talking about the experimental proof for it in terms of the Stern-Gerlach experiment, what spin is not, and why it's such a strange kind of thing that it's hard to visualise, at least in our kind of very visual, classical kind of minds. And then we'll be talking about, well, what equations predict spin, looking at the Dirac equation, and we'll be seeing how the Dirac equation relates to a group of matrices called Pauli matrices, which are matrices representing the spin of particles. Spin is vital because spin tells us about things like electrons really want to be paired, so you want to spin up and spin down electron to cancel out the overall spin corresponding to a really low energy state, and that explains why electrons like to pair up in atoms, thus explaining, for example, the distribution of electrons throughout an atom, and this distribution ends up telling you about kind of like how many electrons you end up with in the shells that orbit furthest away from the nucleus, and that has huge impacts upon the chemistry of atoms, what kind of bonds they form. So chemistry is hugely impacted by spin. Spin also explains how electrons can behave like tiny magnets, thus explaining how objects can maintain being magnetized even when away from a magnetic field, thus kind of explaining how your compass works with your needle on the compass. So in terms of navigation, in terms of the chemistry that leads to life itself, spin is hugely important. And given how abstract spin can be, and how confusing spin can sometimes be when it's introduced, I thought it was worth doing a video just about spin. So this is going to be all about spin. If you like this video, then have lots of other videos on my channel where I go through other features of particles, quantum mechanics, relativity, and all that jazz. So the first direct kind of piece of experimental evidence for spin was an experiment called the Stern-Gerlach experiment. And the Stern-Gerlach experiment is actually quite important generically in quantum mechanics because it showed fairly concretely many principles behind quantum mechanics, such as the very physical existence of, quantum mechanical or superposition states. So the Stern-Gerlach experiment was hugely important in kind of showing clearly that the principles of quantum mechanics work, but it also really showed that kind of particles have to have a property called spin. And what we'll look at now is how the Stern-Gerlach experiment shows this. So in the Stern-Gerlach experiment we have a source which is producing a beam of silver atoms, and the silver atoms are travelling in a straight line from our source. And as they're travelling, they pass through a non-uniform magnetic field. And it was observed that the silver atoms deflect, and it's this deflection that is evidence of spin. And to see why deflection indicates spin, we have to think about, well, what would happen if we ignore spin? Well, we know that kind of atoms generically, including the silver atom, are neutral, that is, they have no electric charge. And you might think, well, silver atoms having no electric charge won't be deflected by a magnetic field, because we know magnetic field deflects moving charges. But an atom is by definition neutral, so electrically neutral, so it has no net charge associated with it, so you might think it shouldn't be deflected. And we know the silver atom is neutral because for anyone that's, come in contact with silver leaf or silver plated cutlery, you'll know that you don't get an electric shock when you touch it. So the atoms the silver is made up of can't be electrically charged. So we might from that think, well, okay, nothing's going to happen to the silver atoms. They're going to continue travelling in a straight line and the magnetic field will have no effect. However, we know if we think more carefully that a silver atom is actually made up of a nucleus where most of the mass of the silver atom is concentrated, and electrons, which if we're using a semi-classical model, we can think of as orbiting this nucleus. And we call each kind of possible orbit a shell, or energy level, because each electron in a particular shell will have the same energy. So we also call a shell an energy level. And the electrons are charged. And moreover, not only are they charged, but the outer electron, so the electron in the shell furthest from the nucleus of a silver atom, is all by itself, or in other words, it's unpaired. And because it's all by itself, essentially all the angular momentum of the silver atom is associated with that electron. So we might go, well, okay, if the electron has kind of orbital angular momentum, in other words, it's orbiting the nucleus, then because there's kind of an electron in the outer shell for a silver atom, maybe this electron is actually essentially orbiting or acting as a moving charge, and therefore this electron will be deflected by the magnetic field and it will carry the whole atom along with it. Thus we would expect a silver atom to be deflected by the magnetic field. And indeed, if the outer electron of a silver atom had orbital angular momentum, then we would expect silver atoms to be deflected, and we wouldn't have to worry about adding another type of angular momentum, or in other words, adding spin to our description of what's going on. However, from a more full quantum model of the atom, we know that we can't really think of electrons as orbiting the nucleus. And that's because the idea of position is a little fuzzy in quantum mechanics because of Heisenberg's absurdity principle. So really, electrons and particles in general behave like waves. They behave as if they're actually distributed out in space. And the mathematical object that describes the shape of this wave is called the wave function. It's a solution to Schrodinger's equation. And the wave function for kind of an outer electron, if it's all by itself in an atom, is a wave function that describes a particle with a no orbital angular momentum. In other words, in a more full quantum model of the atom, which we know is better, more accurate than a semi-classical model, the kind of outer electron in a silver atom has no orbital angular momentum at all and isn't orbiting the nucleus whatsoever. It's really just an electric cloud sitting there. It's not rotating. Well, the cloud as a whole isn't rotating, or at least the electron is orbiting the nucleus. And therefore, we can't put the deflection of silver atoms down to the outer electron having any orbital angular momentum, but clearly the outer electron has to have some kind of angular momentum, otherwise the silver atoms won't be deflected. And so we say that the electron has actually a different type of angular momentum other than orbital angular momentum. And we call this other type of angular momentum spin. Now, as lots of other pieces of evidence, some direct, some less direct, shows, it's not just the outer electron of a silver atom which has spin. All electrons actually have spin. It seems an inherent property of electrons that they have this new type of angular momentum called spin, including the electrons in the inner shell of a silver atom, many of which also have orbital angular momentum as well. So somehow electrons have to have a type of angular momentum we call spin. And it might be tempting to think of spin as an electron literally spinning, or in other words revolving about its own axis. But in the next slide we'll explore why that kind of idea unfortunately doesn't really work, even though our very classically mooted minds struggle to think of then what spin could possibly be. So we mentioned that electrons inherently have to have angular momentum, and this particular type of angular momentum can't be orbital angular momentum. In other words, it can't be the result of an electron orbiting something or moving in an arc. And actually, if you fire a beam of electrons moving in a straight line that is having clearly no orbital angular momentum, you'll see that they're deflected by a non-uniform magnetic field. I.e., all electrons do have angular momentum that isn't orbital angular momentum. And because our minds are very classically rooted and really want to visualise things, we can really only think of then this new type of angular momentum as being a particle literally spinning. Because our minds can't picture any type of angular momentum that isn't either associated with orbiting dash moving a curve or something spinning. Those are the only two types of angular momentum our minds can really visualise. So we might be tempted to say, well, electrons are literally spinning about their own axis. However, there are a few problems with that. So firstly, if we think of an electron classically, then an electron is often thought of as a point particle, that is a particle with zero volume. So in other words, the electron is kind of a mass, kind of all concentrated at a point. And this mass has together the charge of an electron and so on and so forth. But if the electron is a point particle, then because it has zero volume, it's essentially, well, as the name suggests, just a single point in space. And we can't talk about a point in space spinning. And that's because if we could think of an object, let's say a ball or something, and we could talk about this ball spinning, then we really are talking about identifying 2 points on the ball and imagining them changing position relative to each other as the ball spins. So to talk about something spinning, we need to identify 2 distinct points on that object and think about how those points change as the object spins. But if an electron is a single point in space, we can't define any 2 distinct points on the electron, because the electron is just a single point. So we can't talk about the electron spinning if it's a classical point particle. But you might go, well, actually, we know that classical physics isn't quite right. And if you've done a bit of quantum stuff before, you'll know that actually an electron, as we mentioned before, is described by a wave that is in some way distributed across space. And perhaps we might be able to consider this wave as spinning, even if when we think of the electron classically as a point particle, we can't make sense of it literally spinning. But the problem with this is, whereas with kind of like an atom in its lowest state, where we can indeed describe the wave function, which describes the shape of the wave, using only real numbers, and thus, describing the wave as something we can directly observe. A lot of the time electrons, particularly if they're moving freely through space, have a wave function which essentially describes the shape of this wave, where this wave function is inherently complex. That is, it contains a real part and an imaginary part. And so, in most cases, the wave describing an electron contains real part and imaginary part, and because we can't observe imaginary numbers, it means this wave is actually never directly observable. So it doesn't really make much sense to think of this wave function as literally existing in physical space and spinning, because this wave function is actually directly observable. Definitely when the wave function is complex, which, a lot of the time it will be, particularly for freely moving electrons. So those are kind of very technical points, if you like, over why we can't take the idea of a spin too literally. As in, we can't think of a particle like an electron when it has spin as literally spinning. But there's another more fundamental reason, and in many ways less technical, and that's that an electron has spin as a fundamental property. That is, all electrons in the universe seem to have spin, and the size of the spin seems to be fixed. It doesn't matter what the electron is doing, whether it's forming bonds, whether it's moving through space, whether it's transferring from one object to another. All electrons seem to always have the same size of spin. And what this means is spin, and the amount of spin, is an inherent property of an electron. What it means to be an electron is partly defined by spin. But an object spinning literally, that act of spinning cannot be an inherent property of that object. And I did an experiment to prove this. So here you can see to the left of me is an image of me before I started spinning. And to test whether spinning could be an intrinsic property of something, I tried spinning, and I was like, well, if spinning is an intrinsic property of something, then by spinning, in other words, by starting to spin or changing my spin, I should, suddenly start turning into something different, like I might turn into a dolphin or a unicorn or something. And so to test this, I made a video of what happens when I change the amount I am spinning by. And this is what happened. So you might think from that, well, apart from me looking slightly mad, and perhaps if my parents were going to walk in wondering what on earth has happened to me, I haven't really changed. Nothing much happened in that video. So what we can conclude from that is that an object spinning isn't an inherent property of that object. An object doesn't suddenly start fundamentally changing if it changes the amount it is literally spinning by. So, in other words, since an electron's spin is intrinsic, but spinning is not an intrinsic property, then electron spin cannot refer to an electron literally spinning in physical space. So what is it? Well, it turns out what it is something very mathematical. It's the result of relativity and quantum mechanics uniting and coalescing together. And then when that happens, we start to predict many new things, including spin. And the rest of this video will be devoted to looking at spin as a consequence of uniting relativity with quantum mechanics. And so we'll move on now to looking at why, if we're going to look at an equation where quantum mechanics is united with relativity, we can't just stick with our good old Schrödinger equation, and then we'll be moving on to see, well, actually, how do we unite relativity and quantum mechanics, and we'll be therefore deriving Dirac's equation and then showing that particles with spin is a solution to it. So we mentioned and gave a few arguments as to why spin cannot be associated with something literally spinning. And as we'll see, it turns out that spin is a property which arises when we unite quantum mechanics with relativity. Now, we have a good old friend in quantum mechanics called the Schrödinger equation, which describes the shape of the wave associated with physical matter. So we might really want to try to extract spin, if we could at all, from Schrödinger's equation. But since spin requires uniting quantum mechanics with relativity, for that to work, we would really actually need Schrödinger's equation to be compatible with relativity. And indeed, one of the motivation for producing the equation that results in the theoretical prediction of spin was that actually Schrödinger's equation isn't relativistic, and people were trying to find a way to unify relativity with quantum mechanics, even ignoring the whole spin thing. So why is it Schrödinger's equation relativistic, or why isn't it compatible with relativity? Well, it's worth mentioning what Schrödinger's equation does really well. To be fair to the equation, it explains, if we're ignoring relativity, the shape of the wave, using the wave function, of particles in many systems so accurately, including the wave function of electrons in the silver atom. It describes the possible different shapes of the wave functions. So if you've done A-level chemistry, you'll be familiar with two main shapes. So a spherical shape, and we say electrons with this kind of wave function are in the s orbital, and then you have slightly higher energy electrons with a wave function with a different shape, and we call this other shape a dumbbell shape. And electrons with this wave function we say are in the p orbital. And because the wave functions have different shapes, it then leads to different properties. For example, an electron in the p orbital, so with a dumbbell shaped wave function, is slightly more extended in physical space than an electron with a spherical wave function, and therefore electrons are slightly more exposed if they're in the p orbital, and that means bonds caused by electrons in p orbitals tend to be more exposed, and therefore kind of encourage more reactive chemistry, if you like, than bonds associated with electrons with spherical wave functions. So this has very significant effects, and it's actually this that is responsible for double carbon bonds making a molecule more reactive than single carbon bonds. So, although Schrödinger's equation just in principle explains the shape of the wave, this has ramifications throughout chemistry. And in physics, the shape of the wave tells you about diffraction patterns, about lots of stuff. So Schrödinger's equation does a lot right. And so we might really want to use Schrödinger's equation, but sadly, is it compatible with relativity? And the reason it's not compatible with relativity is that Schrodinger's equation doesn't treat time and space on equal footing. So Schrodinger's equation relates how the time and spatial parts of the wave function are connected. It tells you about the relationship between them. And the thing is, the spatial part really talks about the second derivative of the wave function, so how the wave function curves in space. Whereas the time-dependent part of the wave function only includes a first derivative in time. So it doesn't tell you about curve in time, if you like to put it that way. But essentially, the Schrodinger equation is, if you like, symmetrical in time and space. It has a second-order term in space, but a first-order term in time. And we see this if we look at Schrodinger's equation directly. So this is Schrodinger's equation in its full glory. Psi, which is that trident-like symbol, is the wave function. And it's a wave function of three-dimensional position described by your vector r and also time t. And Schrodinger's equation allows you to work out the wave function, particularly if you have extra kind of conditions imposed by the environment constraining solutions of this equation. But Schrodinger's equation has a first-order derivative in time and a second-order derivative in space. And what that tells you is that the wave function that originates from Schrodinger's equation originates from an equation where we can't unify time and space into one term. In other words, Schrodinger's equation inherently thinks of time and space as different to each other, and therefore we can't unify time and space into space-time. And relativity is all about space-time as a single object. And things like time dilation, length contraction, phenomena associated with relativity all come down to thinking about space-time as a single object. So really a relativistic equation should be an equation in terms of space-time and thus have a single term describing time and space as kind of one term. Not two separate terms which we can't unify into one. So that's why Schrodinger's equation is not relativistic. We cannot write it in a relativistic form. So we mentioned why Schrodinger's equation doesn't really work. It doesn't talk about space-time. It doesn't unify time and space. And the thing about not unifying time and space is you miss out on so many ideas. And also there's a lot of geometric beauty if we unify time and space. For example, if we unify time and space in space-time, we can think of two light cones, a past light cone and a future light cone. And because the speed of light measures how quickly information can travel, it turns out that these light cones contain all events. There's anything that has or could happen, which could have in the past impacted you or impact you in the future. Or equivalently, you could have impacted in the past or you could have impacted in the future. So in other words, your whole, not just history, but all of your possible histories is encapsulated in these two light cones. And these light cones kind of emerge from the point in space-time you are currently. So where you are in space and also the current time. And that, again, makes the idea of thinking of, well, where you are in space-time, in other words, forward position. I say forward position because it's where you are in 3 dimensions of space and 1 dimension of time. um, very neat if we're thinking of light cones and all possible histories and futures. So, as well as there being deep physical reasons to consider time and space as being united, there's beautiful geometry and elegance which emerges from it. So, really, a fundamental equation should, both for very deep physics and also aesthetic reasons, unify time and space. Even if the equation mentions time and space separately, it should be able to unify them together into a single term, such that there's a term in an equation that talks about space-time, and, we don't have incompatible terms of space and time. So, that's why Schrodinger's equation doesn't work. So, if we try and unify quantum mechanics and relativity, well, starting off with quantum mechanics didn't really help us. So perhaps let's start off with relativity instead. So a relativistic equation, an equation in relativity which talks about the energy of a particle, is this equation that says that the energy squared is equal to the momentum squared plus the mass squared. Now, the energy of a particle has to depend upon both mass and momentum. And that's because, say we take an object with mass or an atom with mass. Well, objects with mass can be converted into energy. And we can see that because the sun, for example, is actually very, well, in proportion to its total mass, it's very slowly losing mass. But in terms of what we would think of as a lot of mass, that the sun is losing an astonishing amount of mass. What we would think of as an astonishing amount every single second, because it's converting that mass into energy, and thus kind of providing energy to the Earth, allowing for the development and sustainment of life. So this equation helps explain how civilization can survive, really, how energy is kind of produced in the sun. So energy has to, at least in part, depend on mass, but energy also has to depend upon momentum. We know this for a couple of reasons. So firstly, if we think about an object, when an object starts moving, it has more energy than when it was stationary. So in other words, when it starts to have momentum, the object starts to have more energy. So clearly, the amount of energy must increase if we put in some more momentum into the system. So energy has to depend on momentum. The other reason why energy has to depend upon momentum is if we consider particles without mass. So, for example, particles of light, which we call photons. So photons or particles of light don't have any mass, and we know this because light doesn't fall to the ground. However, we see in experiments that particles of light, so photons, can bounce off things, kind of like snooker balls. And so photons must have some kind of momentum, and indeed our equation that we have here predicts that photons must have momentum because they have energy. And our equation clearly goes, well, if a particle has energy, even if it doesn't have mass, it will still have some kind of momentum. Although for photons we have to use a different type of momentum than, non-relativistic particles with mass. So, there's a lot of physics instilled into this equation, but essentially this equation unifies energy, momentum, and mass, and it's predicted by relativity and therefore fully compatible with the idea of space-time. So we're going to start with relativity, this equation, and now we're going to bring in quantum mechanics, because as a reminder we want a theory that unites quantum mechanics and relativity. Well, we can bring in quantum mechanics by thinking how we think about energy and momentum quantum mechanically. So, at least in non-relativistic quantum mechanics, so that is for our purposes, Schrodinger's equation, the state is described by a wave function. And you can get the energy of a particle in a particular state by, in some cases, by taking the time derivative of the wave function, so seeing how quickly the wave function changes with time. So we can think really of the time derivative, first order time derivative, as being associated with energy. But what about the first order space derivative? Well, as we can see if we play around with Schrodinger's equation a bit, the first order space derivative is associated with the momentum of the particle. Now, in non-relativistic quantum mechanics, the state is represented with a wave function. It turns out if we bring in relativity, we can't really talk about the state in terms of a wave function anymore. But the idea still holds that the first order derivative of the state tells you about the energy associated with that state, and the first order space derivative of that state tells you about the momentum associated with that state. And so if we want to now have a relativistic quantum mechanical equation, perhaps we should replace energy with a time derivative, momentum with a space derivative, but have them related in the way they are here. So that would be a sensible thing to do. Now you might think that we haven't got an equation that directly relates E with P. We've actually got an equation that relates E squared with P squared. So you might think that we actually want our fundamental, that is quantum mechanical relativistic equation, to be an equation which is second order in space and second order in time. And this was actually attempted, but when you do that you have issues with predicting negative probability. So it turns out we actually want a first order with time and a first order with space. And we want to relate those two together in a way that is compatible with this equation. So really we want to start with this relativistic equation, turn it into an expression which depends on energy and momentum rather than energy squared and momentum squared, and then replace energy and momentum with time and space first order derivatives. So that's kind of where we're heading. So as I say, we really, to start off with, want to get an expression of the form energy equals momentum plus mass. And for those of you which have done lots of algebra before in terms of expanding things, you might say that there seems to be an initial problem if we want an equation that energy is something like momentum plus mass, but we want it to be equivalent to our top equation here. And that's to do with cross terms you will get when you square both sides of our bottom equation. And we'll come on to that in the next slide, but as an exercise, if you like to do a bit of maths, see if you can see where there might be a bit of a problem, at least at first, if we claim that the top equation and the bottom equation are both true. So, as we mentioned, there is a problem, it seems, with claiming that energy equals momentum plus mass, which we would like to have a equation which deals with space-time but is first order in time and space. With our kind of key relativistic equation, which is energy squared equals momentum squared plus mass squared. And to solve this, we're going to have to bring in, it turns out, matrices. And indeed, one reason doing this video was that kind of currently doing a playlist on linear algebra, which includes very heavily the study of matrices. So if you're unfamiliar with matrices and would like to check out how to work with them and how to do algebra with them, there's some videos already available on this channel, and also there's lots of videos on matrix algebra on other channels. We're not too concerned with the exact details of matrix algebra, but it's worth saying we are going to have to bring in matrices to solve this problem. So have you worked out the problem? Well, the problem is that if we consider, energy, momentum, at least the size of momentum, and mass all as numbers, we do have a contradiction. Now to show this contradiction, we can bring energy and momentum terms to one side of the equation. So if we start with energy equals momentum plus mass, and we can rearrange it to energy minus momentum equals mass. But then if we square this, we don't end up with E squared minus P squared, which is what we would need for the equations to be equivalent. So we seemingly have a contradiction. So what do? Because we don't want energy squared and momentum squared, because we don't want second order derivatives, because that results in negative probabilities. So what can we possibly really do to solve this? Well, what we can do is we can realise we don't really need an equation exactly of the form energy equals momentum plus mass. We don't need an equation that is exactly energy equals momentum plus mass. We just want it in that kind of form to allow us to use first order derivatives for both time and space. So we could, for example, put coefficients in front of energy and momentum, and the form of the equation would be preserved. And if those coefficients, so let's call them alpha and beta, are matrices, then in fact we can have the statement that alpha times energy equals beta times the size of momentum plus mass to be exactly equivalent to an equation that boils down to energy squared equals momentum squared plus mass squared. But for this to work, clearly alpha times beta can't equal beta times alpha, otherwise we end up with a contradiction. But the thing is, with matrices, the order you multiply them can matter. So if alpha and beta are matrices, it's entirely probable, and indeed if we picked matrices at random, it'd be very likely that alpha times beta wouldn't equal beta times alpha. And if we pick alpha and beta sensibly, then we can actually have our two equations being consistent with each other. So we really want alpha and beta to be matrices. So introduced matrices, but our next kind of question is, well, how can we combine these matrices together? Can we, unify them? Because energy and momentum, for example, can be unified in special relativity, because we can think of energy and momentum as actually components of a single vector called form momentum. And actually the significance of energy squared minus momentum squared equals mass squared is really that the scalar product of this form momentum is mass squared. And if you've done scalar products before, you'll know that a scalar product is preserved even when we change our kind of coordinate system or change our axis. We're describing the components of the vectors in. And therefore, really, the significance of energy squared equals momentum squared plus mass squared is that is essentially there's a vector called form momentum, and the size of form momentum is equal to the mass of the object with form momentum, and all observers agree on mass because the scalar product it stays the same even when you alter your coordinate system. So energy and momentum are parts of the same vector and unified, so we might think that there's some way to unify alpha and beta. And that will lead us onto a path to talk about gamma matrices, and then we'll see that gamma matrices are made out of Pauli matrices, and it's Pauli matrices which kind of represent the spin of our particle. Hello, so I've changed the location briefly for this slide. I'm doing it in a slight out of order. I'll move back to the original location for the next one, so I'll seemingly teleport. But as we said, we solved the inconsistency between the equation we want to get to, the special relativistic equation defining energy, which is E squared equals P squared plus M squared, with the fact that we want an equation of the form energy equals momentum plus mass, by introducing matrices alpha and beta. And we mentioned that because we can combine energy and momentum into one vector called for momentum special relativity, it makes sense that we can combine the components of beta matrices and alpha matrix into a single kind of object that will help us unify all of our physics into one. So the question is really, to start off with, how many matrices do we have when we say we have the alpha and beta matrices? Well, you might go, well, we have two, and therefore two matrices to combine together. However, that's not really true. And that's because momentum is a vector of an existing three-dimensional space. And therefore it's three independent components. It has a x, a y, and a z component. And because momentum has three independent components, it makes sense to think that, well, there will be a fairly independent vector matrix associated with each component of momentum. So, for example, if we multiplied our vector matrices with the momentum vector, so P without the arrow just means the size of momentum, but P with an arrow over it means the momentum vector, so the full vector. If we multiplied our vector matrices with our momentum vector, we would get, if we expand it, vector 1 times the x component of momentum plus vector 2 times the y component of momentum plus vector 3 times the z component of momentum, and there's no reason to think that all these vector matrices will be the same. So we have three distinct vector matrices. How many alpha matrices do we have? Well, alpha is a coefficient to energy. Energy doesn't have multiple components, the only component of energy is energy, because energy is a scalar, it's described by a single number. So, as energy only has one component, which is itself, there's only one alpha matrix. So to conclude, we have three beta matrices and one alpha matrix. And when we put all those together, we have four matrices. Now, if we're combining them, we can combine them in many ways. But one way to do it is to put our four matrices kind of into a column. So we have a column with four components, and each component is going to be either one of our beta matrices or our alpha matrix. And we'll call this column the gamma matrix, and we can think of the gamma matrix as almost a vector, so an ordered column of elements, with each element being either one of our beta matrices or our alpha matrix. And we call the components of our gamma matrix the gamma matrices. So the gamma matrices refer directly to alpha and our beta matrices. And you might now think, well, okay, we've got a single object called our gamma matrix, and it has components of alpha and beta, or in other words, the gamma matrices. But how do the components relate to each other? Well, the components have to relate to each other, our alpha and beta matrices, such that we end up with E squared equals P squared plus M squared, which, as we've said, is an equation that describes the length of form momentum, or is about the scalar product of form momentum. And so we should think that there'll be some equation relating the importance of the order in which we multiply alpha and beta, or in other words our gamma matrices, with something that tells us about how the scalar product works in special relativity, or describe some way the geometry of space-time, so how to get the size of a vector in space-time. And the thing that tells us about how to get the size of a vector in space-time is called the Minkowski metric. And the Minkowski metric has a symbol eta, which is like an N with an elongated end to it. And this equation here essentially relates something that tells us in some ways about the importance of the order in which we multiply our gamma matrices to the Minkowski metric. And here the way that we talk about the importance of the order we multiply them is to use something called the anti-commutator, which is these curly brackets. Now it doesn't matter too much exactly what the anti-commutator is. I'm not deriving this equation, but to get an understanding for what the gamma matrices are, and how the components interrelate to each other, we don't need to derive it. But I think it's helpful showing the equation, because it's actually this equation that tells us what specific matrices, if we could use numbers now to represent our alpha and beta matrices, we can use, which will allow us to get to E squared equals P squared plus M squared. And any combination of alpha and beta matrices, or in other words, any kind of sets of gamma matrices which satisfy this condition, will allow us to get to our relativistic equation for entry. And so we're really good. But it turns out a really good matrix to write our gamma matrices in terms of is a 2x2 matrix called, well, a set of 2x2 matrices called the Pauli matrices. And it's actually the Pauli matrices which relate to the spin of the particle, but we can see that the Pauli matrices, one of the reasons they're good is they're simple, but they also satisfy this anti-commutation relation, which is really about the idea that energy and momentum are unified by special relativity, and therefore ultimately about space-time as a single object. And we'll move on to the Pauli matrices in the next slide, where we'll look at actually solving an equation which involves these gamma matrices. So it's really the fact that we have the relationship we had before, which relate our gamma matrices to the Minkowski metric. That means it's sensible to use a particular matrices to write the gamma matrices in. And these matrices, the matrices we use to write the gamma matrices in terms of, are called the Pauli spin matrices. And the Pauli spin matrices, being associated with particles, then lead to the idea of particles having spin. But really, if we're going to think, well, what's a good matrices to use to build gamma matrices, to represent the gamma matrices in, we need to really think, well, okay, what do the gamma matrices look like? And for that, we really need to go, well, okay, if we use our equation that we had, that alpha times the energy minus beta times the momentum is equal to the mass. And we insert the idea that alpha and beta are examples of gamma matrices, and we put it all together, what equation do we end up with? And that would tell us something about what the gamma matrices must look like. Well, if we put it all together, we end up with an equation called the Dirac equation, which is the equation we have here. So we can clearly see that there's gamma. So gamma mu means the muth gamma matrix. We also have a partial derivative, the muth partial derivative. And this partial derivative could relate to time or it could relate to space. And so we have a term that refers to space-time and all in one. You see, we're not individually referring to time or space, we're referring with them together. And we see an I here, and we essentially have an I thanks to quantum mechanics, because the energy is actually associated with in truth, I times h bar times the partial derivative of the state with respect to time. So I comes in because when we're talking about energy, we were thinking of getting it from quantum mechanics, and to get it from quantum mechanics, we have to use the symbol I. Now, I haven't derived this equation, it's worth saying. You can get it from what we've looked at. The important thing is we end up with this equation, and this equation is called the Dirac equation, and it explains so much. I mean, it describes in detail the properties of electrons, so matter particles, and when you combine this with ideas about light, you really lead to a full understanding of how light can interact with matter particles, so how light interacts with matter. And that field is called quantum electrodynamics. And so this kind of Dirac equation we have here is part of the puzzle of why, for example, we can have an electron and a positron meeting and then combining, but then forming a photon, and then the photon can then split into an electron and positron, which recombine into a photon, and then the photon can split off into an electron and positron, travelling their own ways and never meeting again. So there's lots of really complicated physics related to this equation. But this is the equation we end up with. And I've described that we have a partial derivative, which is equivalent in time and space, really. It refers to derivatives in time and space in a single term. We've also got a gamma matrices, which unify, if you like, the idea of energy and momentum into one thing, just as we know from special relativity we should be able to do, because energy and momentum are part of a single four-dimensional vector that exists in space-time. So what's psi? Well, psi represents the state of our system. But it's a state describing the state in four-dimensional space-time, so we might think, well, it has to therefore itself have it has to have four components. So we think of it as a column matrix, or in other words, kind of like a vector with four components. It's worth saying it's not a vector that kind of acts like four vectors. It's a very special kind of vector. So we don't call it a four vector, and to avoid confusion we call it a bispinner. So a bispinner is just the relativistic version of a wave function. It's a way of describing the state of something, but in the context of of space-time. And because our state is, if you like, a four-dimensional vector, particular kind of four-dimensional vector called a bispinner, then for this equation to work, each gamma matrix would have to be a 4x4 matrix. And if you've looked at the rules of how you multiply matrices and vectors together, you'll know that to make this equation make sense, if our state is a vector with four components, then gamma, to multiply it sensibly, must be a 4x4 matrix. And we can think of a 4x4 matrix that is a matrix with, 4 rows and 4 columns, and in each place we have a number, as the same as kind of a 2 by 2 matrix, but with each component itself being a 2 by 2 matrix. Which might sound abstract, but essentially our gamma matrices look something like this. So we see 0, but when we have 0, we really mean a 2 by 2 matrix, all of the entries of which are 0. And we have sigma mu, and sigma mu, each sigma mu is a 2 by 2 matrix as well, and it's a 2 by 2 matrix called the Pauli matrix. So we can think, well, gamma mu is either a 4 by 4 matrix of numbers or a 2 by 2 matrix with components where each of those components is themselves a 2 by 2 matrix. And if you think of the number of terms we have, for a 4 by 4 matrix where each component is a number, and a 2 by 2 matrix where each component is itself a 2 by 2 matrix of numbers, you will see that we end up with the exact same number of terms or components, and we can also end up with the exact same number of rows and columns, so we can always do this kind of thing. It's just particularly helpful to do it in the context of solving this equation if we think of gamma as a 2 by 2 matrix, but where each of its components are 2 by 2 matrices, and we call the sigma mu matrices, we call these Pauli matrices, and they end up referring to the spin of the particle. Now, I apologise if that last slide was a little wordy and a little abstract. It's worth saying we are trying to unify relativity and quantum mechanics, and the Dirac equation is something you won't typically see, at least in a, bachelor's, so a 3-year physics course, although if you love particle physics, you'll probably see it if you do a 4-year physics course in your final year. So this is fairly advanced stuff. But we have seen that we have a Dirac equation containing gamma matrices, and the gamma matrices we can express in terms of Pauli matrices. And doing this will allow the gamma matrices to relate back to that equation that said how the order we multiply them has to be related to the Minkowski metric. So that's really the justification for using the Pauli matrices. And these Pauli spin matrices, if we express the gamma matrices in terms of them, then ends up appearing when we try to solve Dirac's equation, because the Dirac equation is written in terms of our gamma matrices. And it turns out that, at least for a freely moving particle, like a freely moving electron or a kind of outer electron in a freely moving silver atom, the state is an eigenstate of spin. So an eigenstate of a property called spin, and that property is represented as a matrix, because in quantum mechanics we represent properties as matrices, and these matrices are the Pauli matrices. So really spin is a property we get, and this property comes from ultimately saying that we have to relate the coefficients of energy and momentum, so put together essentially our gamma matrices, in such a way that our equation that we would like ends up being compatible with the standard relativistic equation for energy. So that condition, as I say, the compatibility leads to a new property called spin. And you might wonder, well, okay, why does this property act like some kind of angular momentum? And it turns out, well, if you do a bit more in terms of relativistic quantum mechanics, well, really, because of quantum mechanics, we call the energy but really in this case it's more like alpha, our matrix, times the energy. We call that term that corresponds to the energy of the particle the Hamiltonian. And without relativity, because we don't have these, alpha or beta matrices, the idea of energy being conserved and angular momentum being conserved are completely equivalent if we think of angular momentum as just being orbital angular momentum. However, it turns out that if we think of kind of the Hamiltonian now as, as something related to energy, but taking into account our, alpha and beta matrices, then something having conserved energy is no longer equivalent to it having conserved angular momentum unless we stick a little bit onto that angular momentum to include some kind of non-orbital angular momentum. And it turns out if we stick on that thing we stick on, if that thing is spin, which, as we say, arises from our Pauli matrices, then again, thanks to the Pauli matrices, which themselves go back to linking quantum mechanics and relativity, then the idea of something having conserved energy and conserved angular momentum is equivalent. So, in other words, if we're going to insist that we don't violate the conservation of energy, then because of what we said about how quantum mechanics and relativity link, there has to be a part of angular momentum which, if we're going to conserve angular momentum, isn't associated with orbital angular momentum. And that part happens to match the mathematics perfectly of this quantity we called spin. So in other words, spin acts like a component of angular momentum, because without it, angular momentum wouldn't be conserved, even though the math we've used to predict spin theoretically hasn't mentioned anywhere the idea of a particle literally spinning about an axis. It's just said we need quantum mechanics and relativity to be compatible. And, if you want to go into the maths of essentially how you can prove, well, having spin allows angular momentum to be conserved, you use something called the commutator, which is the square brackets you can see in our equations here. And essentially, if the commutator of our Hamiltonian, which represents the energy, and another operator, let's say A, equals 0, then that tells you, well, if energy is conserved, A can be conserved as well. And as we say, without introducing spin, we can't say energy is conserved and angular momentum is conserved. So in other words, essentially we have to introduce spin to say, well, the commutator between the Hamiltonian and angular momentum, so orbital angular momentum and spin, is going to equal 0. So I hope this video has been enjoyable. It's worth saying at points it's definitely been me being very hand-wavy with the mathematics. But, well, that's quantum mechanics and relativity for you when you bring them together, unless we're going to go into immense detail. But, part of this channel is, sharing physics and making it more accessible, but I'm also hoping, some people that watch this channel may be motivated to do a course, say on, advanced particle physics, where you'll derive the Dirac equation properly and go through this all rigorously. But I hope this video has been helpful in showing what spin is, what spin is not, and also it's hopefully shown you that by uniting bits of physics like relativity and quantum mechanics, we can end up predicting not just new tiny features, but whole new properties of particles, which has ramifications, in chemistry, for example. So it's ultimately spin, which comes from mathematically the Dirac equation. So in a sense, it's a Dirac equation that explains, at least in part, how chemistry can happen as we see it happens, and therefore how I can exist making this video and you can exist watching it. So, the Dirac equation might sound abstract, but it's fundamental to our very existence, as to the existence of, well, at least behaviour of all matter particles. So, I hope this video has been fun, and if you've liked this video, consider liking it or sharing it to help more people save the video. Always welcome to any comments, anything you might like me to change, or any other videos you might like me to do, or anything that went particularly well in this video. Helps me make better content and content you'll enjoy. So, and hopefully see you for another video soon.